use Laplace transforms to solve the following initial value problem. We have this ODE and two initial conditions. Okay, let's take Laplace transform of this ODE. Then we get Laplace of y double prime plus Laplace of y equals Laplace of this Dirac delta function. Okay, so Laplace of delta t minus pi plus Laplace of 1. Okay, let's look at the table and find the Laplace of second derivative. This is s square Laplace of y minus s y at 0 minus y prime 0. Okay, it's not needed, but I put the brackets anyways, plus Laplace of y is just Laplace of y equals Laplace of Dirac delta function t minus pi is from table e to the negative pi s. Okay, e to the negative this shift s plus Laplace of 1 is 1 over s. On the left we can factor Laplace of y from these two terms, so s is square plus 1 Laplace of y, and use the initial conditions. Y at 0 equals 0, so this is 0, so s times 0 whole thing is 0, y prime 0 is also 0, so nothing left by the way, equals e to the negative pi s plus 1 over s. Now let's divide by s square plus 1 to isolate Ly. So Laplace of y is equal to divide by this, so we got two terms, so e to the negative pi s over or 1 over s square plus 1 plus divide this by s square plus 1, so 1 over s times 1 over s square plus 1. Okay, then we now take the inverse Laplace to recover y. So y as a function of t will be then inverse Laplace of first term e to the negative pi s times 1 over s square plus 1 plus inverse Laplace of 1 over s times 1 over s square plus 1. Now look at the table and find the inverse Laplace of e to the negative pi s times 1 over s square plus 1. We know Laplace of sine t is 1 over s square plus 1. Okay, this is the Laplace of sine t, and e to the negative pi s, this is coming from this will be the Laplace of unit step function. Okay, so they are together, so this will be sine t, but we need to shift to the pi to the right, so this will be sine t just from this one but minus pi. It will be a shift to pi to the right, and this is coming from the unit step function e t minus pi. Okay, u t minus pi unit step function, that will be e to the negative pi s, and this is sine t, but we need to shift to the right, plus now we need to take the inverse Laplace of 1 over s times 1 over s square plus 1. This is times. We can use the partial fraction decomposition to write this product as a sum of two fractions in this way. This can be written as a over s plus s square plus 1, let's say bs plus c, and find the values of a, b and c. Then when we find the inverse Laplace of a over s, a is a constant, so inverse Laplace of 1 over s is just 1, and we need to separate into 2. That's one way. Or since we know the convolution theorem, let's try to use convolution. The inside, let me write Laplace inverse 1 over s is Laplace of 1, let me put that, times 1 over s square plus 1 here, that's the Laplace of sine t. Okay, this is Laplace of sine t, and we have to take inverse Laplace. this part is done sine t, but due to this shift pi to the right, unit step function u t minus pi plus. Now we have product of two Laplaces, and when we take inverse Laplace from the convolution theorem, this becomes 1 convolute sine t. Okay, because when we take the Laplace of 1, we have this. Laplace of this convolution will be product of Laplaces. Okay, what I was trying to say, when we have Laplace of a convolution b, that will be Laplace of a times Laplace of b. Now we are going other way around. We are taking inverse Laplace of this product here. That means a convolution b. Now we need to find the convolution of 1 and sine t. Okay, so this is already done. Ut minus pi plus, from definition this convolution is given by 0 to t, first function at t minus v, this one is 1, and sine v dv. Let's evaluate this, then we get the final answer sine t minus pi u. It's a heaviside function or unit step function, and this will be plus, let's do it over here. Antiderivative of sine v is cosine v, in fact negative cosine v, and we go from 0 through t. Negative cosine t minus negative means plus cosine 0 1, so 1 minus cosine t. So this is 1 minus cosine t final. That's the y function.